Hey, good morning, everybody. So, Yttrium, right? Probably not had an undergrad course, or maybe even a graduate course, where you talked a whole lot about Yttrium. It's not a super common element that people would think about because it has that probably misnomer of rare earth or actinide. It's you're kind of taught to think like that lower group three that's not really transition metals. It's these weird like actinide things that don't have a whole lot of usages. But I'd love to tell you today that they actually do. So yttrium, one of seven actually of these elements that occur in a mine in Ytterby in Sweden. It was discovered in 1794. It wasn't isolated until 1824 because of its amazing ability to complex with other elements with similar chemistry, similar radius. So seven other elements were found in the same rock clusters and mineral clusters in this mine. Most of them were either actinide or lanthanide or scandinide. So it has a whole lot of really cool properties for metallurgical chemistry and ceramics. So it appears most commonly in nature, about 50% concentration of actual yttrium is this mineral xenotime, about 3 to 5% as this mineral monazite. But most of the extraction in the world comes from South Asia and China, and a little bit from Brazil. It's where most of the American supply comes from, those two different regions of the world. Though it appears a lot in that town in Ytterby in Sweden, in Scandinavia as well, hence Scandinide, where they were discovered. So these natural allotropes, that crystalline structure, that is, you can see in a figure 2, that's a yttrium 3 oxide, which is what monazite is. It has that nice octahedral structure, which is very interesting to see complex and stabilize other metals in ceramics. But it's used for medical lasers. You can see in figure 3 there, when you dope about 1% neodymium by mass with yttrium aluminum garnets, you get these layered crystals that you can use for solid state lasers. And then in figure 1, the yttrium barium copper oxide superconductor, which is a high temperature superconductor. Doesn't mean it's room temperature, doesn't mean it's much higher than probably the boiling point of liquid nitrogen, like most superconductors are. But it's going to be more and more useful as we continue to research higher and higher and higher temperature superconductors. So its electron configuration, 5s241 base krypton, which leaves behind a very stable 4p6 3d10 4s2 configuration. So it's almost never not in a +3 oxidation state. Be it in nature, be it in a complex, it's almost always going to have that +3 oxidation state. Its most common allotrope is 50 neutrons, or isotope, 39 electron, 39 proton, 50 neutrons. Ionization energy, somewhat low, 6.27 electron volts, which we would expect for something that has a +3 oxidation state most commonly. Electron affinity, 29.6 kilojoules per mole. And then electronegativity, 1.22 on the Pauling scale. It's about common. It's in between francium and it's in between fluorine. So would make a lot of sense. Then it displays contraction from 2.27 angstroms to 1.02 angstroms at its +3 oxidation state, which makes it perfect for kind of hiding in these similar mineral deposits as other lanthanide metals, other scandinide metals, which is why in yttrium, that same mine is where a lot of these other elements were found, is that you would get like scandinide scandium oxide, yttrium oxide, cerium oxide, that these different deposits would contain multiple different abundances of these metals, just because they would share similar oxidation states, but also similar metallic properties, similar mineral properties, because the density is the same. Those crystalline lattices they're forming are going to be very similar. Though different than other transition metals, yttrium has these odd lanthanide properties. It experiences lanthanide contraction, which you don't really see with transition metals. It's somewhat uncommon. So it has a density of about 4.47 grams per centimeter squared, very similar to titanium, about 4.5. However, you're not going to see aircraft made out of yttrium like you would titanium. It's more than double the price per kilogram, which comes down to natural abundance, import-export cost. Titanium is $12 a kilogram. Yttrium's $35 a kilogram. And titanium is much more difficult to isolate and extract at a large scale than yttrium is. In fact, when you are extracting and isolating yttrium from xenotime, which is where most of its abundance is, when you are industrially extracting yttrium, you're going to do the first step, isolating it from the phosphate there's a sulfuric acid treatment, which is the most common, and there's like ion exchange. But the second stage is actually converting that xenotime to monazite, where it's a yttrium oxide. And then you would continue with the monazite extraction. So like most transition metals, it's going to have like a soft white silvery presentation in nature. That's just what it's going to appear as. So we don't see, like I said, very similar to transition metals, but also displaying some unique characteristics. So then in a periodic trend, very similar melting point to iron, titanium, scandium, cobalt, but yttrium's got a significantly lower electrical conductivity than other transition metals. But it has this cool property of that lanthanide contraction, its oxidation state, that it has trivalency, that it can move 3 electrons. So it's a big candidate to replace things like lead zirconate or titanate for supercapacitors, because it has those it has the propensity to form lattices that are very similar, and it can stabilize those lattices. So for ceramic supercapacitors, maybe seeing a lot more usage of yttrium, which is what we propose would actually be continued for research. It's a strong candidate for it based on these properties. Now, a really interesting reaction that is very uncommon to transition metals is that yttrium actually forms oxides in water at room temperature. So if you take finely ground yttrium and add it to water, it'll actually start producing hydrogen gas as it forms yttrium hydroxide. And you get this almost like the rainy nickel or a palladium or platinum type catalytic reaction. But instead of it coming off of hydrocarbons, it's coming just right off of water, which is very, very, very cool. Again, is it a lanthanide? Is it a transition metal? It bridges the divide between those two. Again, with its radius being so similar in angstroms, about plus or minus 10 from almost all actinide and lanthanide metals, you can do some really cool coordination chemistry. Like I would love to see down the line us producing some work with different lanthanide and actinide ceramics. So just see what kind of properties they have for be it crystal or be it supercapacitor. As we stated earlier, with this neodymium doped yttrium aluminum garnate solid state crystal, you get a nice peak at about 1063 nanometers, which is deep tissue. At a lower wattage, it can be used as like a hair removal laser. At higher wattages, it's great for ocular surgeries and for removing scarring. At even higher, depending on if you're using, instead of an LED lamp, if you're using a xenon arc lamp for your electron source, it actually is used for oncology. Has a lot of cancer fighting effects for oncological surgeries, which is very neat. So perhaps yttrium can form similar ceramic supercapacitors like lead zirconate titanate. We would propose chiefly that our goal going down the line in the future would be to replace lead zirconate titanate, just so we can reduce the amount of lead exposure overall in the electrical world and in critical infrastructure. But that is all I have for you today. I would love to answer any questions you might have. Thank you.